let's keep moving on. So that's the first point in our summary outline that we started this video or video series with. Now on to the next thing. If you remember, when we were talking about weak acids, we said that they have an equilibrium. Okay, their dissociation reaction has a reversible part to it. You have a double arrow, and therefore we can write an equilibrium equation for that dissociation. So here's an example of a weak acid, HA. It's just a general abbreviation for an acid with water, and as this acid dissociates, because water is playing the role of a base here, it's going to grab this hydrogen from HA. What's left over is A minus. There's the conjugate base, and the hydronium ion, the conjugate acid. And let's write an equilibrium expression for this reaction. If you remember from chapter 7, equilibrium constant, K, equals the concentration of products divided by the concentration of the reactants. Okay, this is for any equation we have an equilibrium or a reversible reaction for. So if we're going to write an expression for K for this reaction, let's do that now. K equals, we'll start with the products on top, and remember that you put the concentration, you put brackets to indicate concentration. So the concentration of, I'm going to zoom in so I can write smaller, H3O plus times the concentration of A minus, and you would raise it to the power of its coefficients. Here our coefficients are all 1 for all the reactants and all the products, divided by the concentration of our reactants, HA, and concentration of H2O. Okay, so there is our equilibrium expression for this weak acid. Okay, now let's look at these statements down here below it. Let's look at the first one. Even though water is a reactant, it is also the solvent for this solution. Well, what does that mean? It's a reactant and it's a solvent, so what? Well, because of that, because water is the solvent, its concentration is much, much greater than that of any other reactant or product in the whole equation. Okay? The significance of this, what that means, is statement 3. The concentration of water will not significantly be affected when the acid dissociates. So, for example, I'm going to move this down here. If we wrote out some concentrations, let's say our concentration of the acid, remember we write concentrations with units of molarity. Okay, molarity being moles of solute over liters of solution. We abbreviate molarity with an M. So let's say our concentration of the acid is like 0.5 molar. Okay, put brackets around that. Well, what that would mean for water, because we have so many more water molecules, we have a ton of water in this reaction because it's the solvent too. And the solvent, remember that the solvent, where do I want to write this? In any solution, the solvent is the chemical present in greater amount. So there's two parts to any solution, the solute and the solvent. The solvent is always the thing present in greater amount. So because water is the solvent here, and it is for any aqueous solution, and anytime you have an acid that's dissociating, it's going to be in water, we could say, I don't know, make up a really high number. Let's say it's 20 molar. I mean, that's just crazy high, but that's probably realistic. If this is a weak acid, we don't know exactly how much will dissociate. Let's say around 50% dissociates, okay, and we have half the concentration left. Then what we would end up with is 0.25 molar of this left over, okay? And we would make, so we would no longer have this, we would make 0.25 molar of these products. Okay, now how much would the concentration of water be affected? Well, every time one of these HA molecules, every single time our HA molecule dissociates, we're going to react it with it's going to use 1 molecule of water, okay? 1 molecule of acid reacts with 1 molecule of base, which here is the water. And so you can see when all's said and done, maybe the equilibrium concentration would not be affected very much for water. It'd still be really high. So compared to everything else, the concentration of water is not changing very much. Okay, that's what we mean by point 3. The concentration of water is not significantly affected. Because of this, we're going to make an adjustment to our equilibrium equation, K. And this is just for weak acids. The adjustment we make is statement number 4. What we're going to do is we're going to group water, concentration of water, with K. And we're going to rewrite this, and we're going to call it the acid dissociation constant, K, and we're going to put a little a right here to indicate that we are talking about weak acids. All right, so this is not your normal. The normal K is just reactants over products, no adjustments. This is now Ka, and so look at what we've done here. This equation on the next slide shows it. We took water out of the denominator and we moved it over here. And we're doing K times the concentration of water. Essentially, don't worry about the multiplication that's going on over here. Just know we take water out of the equation. Okay, the end result is we remove the concentration of water from the equation. We don't put it in, okay? And we call this K times the concentration of water. We call it Ka. So what we get is that Ka equals products, concentration of H3O plus, times concentration of A minus, divided by the concentration of the acid, HA. Okay? These are the products. This is the reactant. Okay? We do not have water in our equation. That's how Ka is different from a normal K. All right? Now, follow-up question to see what you gathered when we were talking about the strength of acids. Why do we not write Ka for strong acids? Before I answer this, I want you to think about that. Why do we not write Ka for strong acids? Maybe you have the answer in your head. Maybe you write it down on your notes. If you don't know, let's go back to the slide where we were looking at the strong acid and the weak acid here. Remember, for a strong acid that we have a single arrow, okay? Because, why is that? We said strong acids completely disassociate in water. We do not get a reversible reaction. And you can only write, so the answer is strong acids completely disassociate. I'm going to abbreviate. There is no reversible reaction. And in parentheses, I'm going to put single arrow to help you visually remember. We cannot write an equilibrium expression unless we have a reversible reaction, okay? So equilibrium, I'm going to abbreviate EQ. Well, actually, it should be capital Q. EQ, equilibrium expression, is only written for reversible reactions. Okay? Strong acids are not a reversible reaction, or I should say the disassociation of